In this video, we're going to introduce the idea of number systems. Now, we're already familiar with number system in base 10. We have 10 fingers, right? So it makes sense that we would, as human beings, evolve to count in tens. Now, understanding how these basic number systems operate is really critical in helping us make sense of how we convert between number systems. In particular, we want to think about how it is that we deal with number systems in base 10. So we, of course, know that we can count quantities between 0 and 9. And so we could say that right now we have 0 elements on the screen. And now we have 1 element on the screen. And now we have 2 tick marks, which we can represent with 2, and 3 tick marks, which we can represent with 3, and so on until we get to 9. And now we have 1, 2, 3, 4, 5, 6, 7, 8, 9 tick marks. And I'm not going to group them in 5s, I'm going to group them in 10s. So then, of course, the next number, well, we're out of numbers in the number system. We can only count from 0 to 9. So the fact of the matter is that we have quantities that are larger than 9. So how could we possibly represent that? Well, once we get the next element, which we have our 5, 6, 7, 8, 9, 10, we represent that by saying, well, now we have 0 ones, and we keep track of the number of groupings of 10 that we have by incorporating a digit right next to that. So we call that number 10, but what the number 10 really means is that we have one grouping of 0 through 9 and one more. And in this sense, we can then think about how many 10s that we have. So of course, if I just represent this as a 10 and another 10 and another 10, then really I have 3 of those 10s and I have 0 individual 1s. Right? So if I add a couple of 1s, those 2 1s I can represent with a value that's already in base 10, but I have no way of keeping track of these 3 groups of 10 because, again, I've run out of numbers. So that's where we incorporate this digit to the left of our counting the 1s in terms of the number of groups of 10 that I have. And this may seem obvious, this may seem like something, yes, we've already learned this before, but it's a really important thing in terms of understanding how to convert between number systems. So when you have 0 through 9 and you run out of elements, you incorporate one additional element that keeps track of how many of those groupings you've already created, and then you can reset your counter for counting the individual ones. In this same sense, we can also think about binary. And with binary, we only have 2 possible values. So imagine that you have only 2 fingers. And so that you could keep track of either a 0 or a 1. So this is what we call a base 2 number system. Okay, so the reason we want to think about base 2 number systems is although we have 10 fingers, a computer can really only keep track of a high or low signal, which we often represent as a 0 or a 1. So if we're going to design computers that can do arithmetic and that could store things in memory, we have to adapt to this idea of a binary system, bi meaning 2. And so when we think about binary systems, if we think analogously to how we would do this up here with base 10, well, in the sense where I have nothing, I have no elements, just a blank element, I can still represent that with 0. I have 0 tick marks. Now, when I have 1 tick mark, of course, I could represent that with a 1. But now, what about a 2? What if I want to represent the fact that I have that many tick marks? Well, in terms of grouping, rather than creating 2 hash marks, what I'll say is that every time I run out of digits, I'm going to put a strike through this element here, just like we do up here. And what I will do is I'll say, well, we have 0 individual tick marks or hash marks, and now we have 1 grouping or 1 pair of 2. And now if I were to say, well, I have 1 grouping of 2, and then I have an individual tick mark, well, then I could represent with a 1 over here to say I have 1, 1, and I have also one grouping of 2. So we'll say that this right here means one group of 2, and this number here means I have one individual, we'll call it a hash mark or a tick mark. And so really what I'm representing is the number 3, but I'm having to represent it only with zeros and ones. So you might imagine that if I now say, okay, well now we have 2 groups of 2, well, I can no longer represent that here with this 1 because I only have the numbers 0 to 1. So I have 0 individual tick marks. I have in this sense created, we can really say that instead of having 2 groups of 2s, and so of course this is illegal because if you're only allowed the digits 0 and 1, then of course 2 is not a number, but I want to have some way of representing that. So rather than thinking about this as 2 groups of 2, what if I thought about this as one group of 4? Okay, so I have 0 individual ticks. I have 0 individual groupings of 2, but I have one grouping of 4s. And I can kind of proceed in the same fashion. So if I have one grouping of 4, and then I have one individual element, I can represent that as saying I have one individual, I have 0 individual groups of 2, and I have one grouping of a 4. Well, what happens once this thing blows up again? What if this becomes our one grouping of 4 and now a grouping of 2? Well, now I can say I have one group of 4, I have one group of 2, and I have 0 individual ticks. And once we run out here, if we were to say, we have, what happens if we have 2 groups of 4 and no individual elements? So again, I'll just put these in here to emphasize that this is 2 groups of 4. Well, I can't do that again because if the third digit from the right represents how many groupings of 4 I have, and I actually have 2 groupings of 4, but I can only represent the number of groupings of 4 as either 0 or 1. Well, what if I took these 2 groupings of 4 and grouped this into one group of 8? So now I can say that I have 0 groupings of individual tick marks. I have 0 groupings of 2. I have 0 groupings of 4, and I have one grouping of 8. And so that leads us to making sense of this in the following way. We could say that this is the number of 2 to the 0 groupings that we have. 2 to the 0 is 1, remember? So that's how many individual tick marks we have. This is how many groupings of 2 we have. It could be 0 or 1. So this is the number of groupings of 2 to the first that we have. This is the number of groupings of 2 squared that we have, the number of groupings of 4. Again, you could have 0 or 1 of them, but if you have 2 groupings of 4, well, that's really one grouping of 8, and guess what? That's the same thing as 2 to the third. So every time you double up, you are creating a new digit in that binary sequence. And in the same fashion, we can also think about a hexadecimal system. And a hexadecimal system is base 16. The digits that we use get kind of strange because we run out of, we can use the numbers 0 through 9. So we could have 0, 1, all the way up to 9. But now we're saying we have 16. So this gets a little strange for a lot of us, but we're now going to use the letters A for 10, B for 11, C for 12, D for 13, E for 14, and F for 15. Now keep in mind that because we're counting 0 in here, this actually represents 16 possible values. Okay, so one way we could think about this now is every time we get a group of 16, we have to iterate over one digit. So of course, if I have 0 elements, if I have no elements, I can use 0 to represent that, all the way up to 9. And 9 elements would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're counting in 16s. And now the integer digit 10, right? So now in base 10, that would represent one grouping of 10. We are in fact going to use, or excuse me, for one grouping of 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm not going to put a strike through it because I haven't run out of groupings yet. I'm going to represent that with the letter A. And then up to 15, 15 will be represented by the letter F. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then now if we imagine we had 16 fingers, now the 16th digit, so if I took all of these guys here, and just copied this down. And now I put a strike through this thing. The only way for me to keep track of this new value is to say that I have one full grouping of 16 elements. One full grouping of 16 elements. So I can now say that this is 1. And now I have 0 individual tick marks. So oddly enough, the number 10 in hex, or hexadecimal, hex for short, the number 10 in hexadecimal is actually the number 16 in base 10. So if I look at base 10 over here, I will say B10. These are, of course, 0 all the way up to 9, and then A is 10, F is 15, and 10 in hexadecimal is 16 in base 10. And in the same fashion, we can proceed. So if I had this one full grouping of 10 here, and then in addition to that, I had one more element, like so, then that's going to be one full grouping of 16 and one individual tick mark. And in base 10, that is actually the number 17. You can do this with any base system. You can do this in base 8. Base 8 would be a very similar flavor. Base 8. We call this octal, by the way. This is the octal number system. And again, imagine that we just now have 8 fingers. So the number in base 10, let's do the base 10 representation. We have 0, 1, 2, 3, 4, 5, 6, 7. And so in octal, in base 8, these are going to be the same. So 0 elements is 0. Now 1 tick mark will be, that means we have 1 tick mark. 2 tick marks will be 2. 3 tick marks will be 3. 4 tick marks will be 4. And then now once we get down here to 7, 1, 2, 3, 4, 5, 6, 7, that's going to be 7 in base 8. Now we know that one more element in base 10, we haven't run out of numbers yet, that's just going to be 8. But in this binary system, or in this octal system, that's one grouping of 8. We've run out of fingers now, so that means we have one grouping of 8, and we have 0 individual elements. So oddly enough, the number 10 in base 8 is equal to the number 8 in base 10. And if we had the same grouping here, and then we had just one more element on top of that, what do you think that would be? Well, that would be 9 in base 10, but that would be one grouping of 8 in base 8, and one more grouping, one more individual tick mark in base 8. So that would be what we would think of as the number 11. So let's add a little bit of structure to this. This is the number of 8 to the 0 elements that we have, right? The number of ones, in other words. And this is the number of 8 to the first elements that we have, groupings of 8. So if we incorporated another element right here, that would be the number of groupings of 8 squared that we have. Going back up to what we had to do here, if we doubled the number of groupings, then we had to create a new column to represent the number of, in this case, groupings of 8. So if we get from 8 to, when we get 8 groupings of 8, 8 groupings of 8 will force us to run out of digits. And so now we want to say, well, we have 8 eighths. Well, that's really just 1/64, or 1/8 squared, one grouping of 8 squared. And any number system we can represent in much the same fashion. Now in the next video, we'll kind of take a look at the structure of how we do the conversions from one numbering system to another so that it's really efficient and we don't have to kind of count by tick marks.